So throughout history, what we know of the atom has slowly changed. From first of all, in like around 2000 years ago, people thought that everything was made out of fire, earth, water, and metal, but obviously we know now that that's actually not true. And what we consider now as modern history kind of started out with the studies of Dalton, and Dalton basically proposed four statements or four theories that he believed was true about the fundamental units of all matter. And basically, the first two that he proposed were actually false, proven false, and the second two, up to today, are considered true. Now, what his first theory was that each element are composed of really small atoms. Now, he believed that these atoms were indestructible, so he thought that they were destructible. So he basically thought that atoms were the smallest unit, and that atoms cannot be split into smaller substances. Now, at first reading this might seem true, but actually we now know that there are such things as subatomic particles. So this actually was not true. So this was proven false when electrons and the atomic nucleus was discovered. Now, moving on to his second theory. His second theory was that all elements are identical. So he believed that in wood, all the atoms of wood was same. He believed that in iron, all the iron atoms were identical, but this actually is also, once again, false due to the fact that isotopes were introduced. So when isotopes were introduced, this statement was proven false, because isotopes show that even in a singular substance, a pure substance, there are various types of atoms called isotopes. Now, the last two theories are actually correct up to today. And his third theory was that the chemical reactions do not, in any situation, create or destroy matter or atoms. So he basically believed that chemical reactions were a mere rearrangement of atoms, which is correct. Chemical reactions do not create new atoms, or they do not destroy previously existing atoms. They simply rearrange them to different ratios and to each other. Now, his fourth and last theory was that atoms combine in chemical reactions usually in whole numbers, so no fractions. And this also is true. We never see a 0.5 of a hydrogen molecule or half an oxygen atom. These just aren't true. They're impossible. So his last two theories were correct, and his first two theories were incorrect. And this is very important to know, because Dalton is quite an important figure in chemistry. Now, when Dalton first discovered this, a lot of people believed it was true. Now, moving on, the second scientist to improve on this idea and add on to the knowledge of the atom was Thompson. Now, Thompson, to tell you the conclusion first, Thompson discovered electrons. So he was the first person to kind of see and prove that electrons existed within atoms. And he did this by a famous experiment called cathode ray experiment. And what this experiment was that he basically had this bottle. such like this. And through electricity, he kind of created a beam in the middle. So let's say this green dotted line is a beam. He kind of projected a line of electricity. This would obviously connect to this side, and this model would roughly look like this. So this electric current would go through this bottle. Now what he did was basically show that when energy was projected in such a manner in a ray, due to the fact that atoms had electrons, these electrons stuck to this energy, so it created an actual visible beam. So at first he only projected not an actual beam but an invisible source of energy, and he projected it through a ray. And when he did this beam of energy formed around it, this light. And you can see this if you search this on YouTube as well. But this proved that electrons stuck to this energy beam and created a visible beam of light. Now, he also improvised on this experiment by adding a metallic or a positive charged substance here and a negative charged substance here. And when he did so, it showed that if we put a positive charged here and a negative charge here, this ray would actually curve kind of like this. So it would kind of curve, instead of a straight line, it would kind of curve like this. And this showed that electrons were actually had a negative charge due to the fact that negative and positive like to stick to each other. So this proved that electrons were in fact or had a negative charge. So Thompson proved two things: electrons, and that electrons had a negative charge. So he proved these two things by the cathode ray experiment. Now, moving on to the third scientist called Rutherford. And Rutherford also found something important through this gold foil experiment. And you probably heard of this, is quite famous. And what he basically did was he had this large panel. He had this sensitive large panel for this experiment. And it kind of went in a circular formation, kind of like this. And he had a projector here. And what this projector basically projected was, this projector would shoot out alpha particles. And this alpha particle is made out of 2 protons and 2 neutrons. And it has a charge of 2+. And this alpha molecule or alpha substance actually isn't on the periodic table, so we just call it this alpha beam. And he also put a gold foil like such in the middle. This gold foil would be here, and he projected this alpha particles, these alpha particles, in a beam. And what happened was that although most of these beams passed through and hit the other wall, so it would hit here, 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 like most of the alpha particles would result in hitting this back part behind the gold foil. Some were bounced off. So some alpha particles bounced off and hit these sides. And this was a very small percentage. So most alpha particles would end up in this area, right? But a few, would end up on the sides. And what actually was happening here is that if we zoom in on this, so if we zoom in on this, what was happening was that within the gold foil, so let's say that this is the gold foil, this area is the gold foil, and basically gold atoms or such like this, and let's say this is the gold foil if we look at it from the side. So there would obviously be atoms of the gold foil like such. And basically what was happening was that although most alpha particles was simply passing through the empty spaces, because atoms are consisted of 99% empty space, a very small percentage was like, so mostly the alpha particles was simply going through, right? But because some alpha particles were bouncing off, Rutherford found out that some alpha particles were bouncing off of something, and these some things were these nucleuses, because alpha particles couldn't have bounced off electrons due to the fact that electrons are constantly moving and aren't very dense enough to bounce off these alpha particles. And these special cases of alpha particles were the ones that bounced off in irregular formations. So basically what Rutherford found was, he found the nucleus, the presence of the nucleus through this gold foil experiment, because when alpha particles was projected through this gold foil, although most of them passed through due to the fact that atoms are mostly made out of empty space, some hit the protons or atomic nucleuses and bounced off. Now through this he found out the nucleus was very dense but also very small, because only a very small percentage of alpha particles would bounce off. And he showed that although the nucleus of an atom was very small, it was very dense due to the fact that it was able to bounce off these alpha particles. Now, after Rutherford, we have two more important scientists. Now, the first scientist was called Bohr, and he created the planetary model of an atom, also called the Bohr Model. And we actually use, although the Bohr model isn't exactly completely scientifically true, because we have found that it actually isn't true, the Bohr model is still very commonly used due to the fact that it's very simple and it's easy to draw. And what Bohr basically found was that he found that electrons didn't actually just randomly wander anywhere. So he basically found out electrons have configurations, and they have orbits, orbits. Now you have probably seen what a Bohr model looks like. So if we draw a Bohr model for helium, there would be an electron here, and the nucleus would be like such, some containing positive protons and some considering neutrons, actually. Oops. Yeah, this would be a classic example of an helium atom. Now, before Bohr, people didn't represent it like this, because people didn't know that there were these rings, these electron shells. They thought there would be a nucleus with protons and neutrons, and people basically thought that electrons would just kind of be surrounding this nucleus in just kind of a random formation without any pattern. And although this is somewhat true, Bohr found out that they had certain areas that electrons would constantly move or orbit around, so he called them orbitals. So he basically found out that electrons do not completely move in random, but they follow somewhat of a pattern, which was called orbitals, because he believed that electrons orbited the nucleus, atomic nucleus. And so basically Bohr found out three things that we have to kind of know. First of all, he found out that electrons are existing in orbitals. Not orbitals, but orbits. Second of all, he introduced the idea that orbits or shells are related to the electron's energy level. So basically, he said that the farther these electrons were from the atomic nucleus, they had more energy. So if there were several rings here instead of two, and the model will be like this, these electrons that are farther from the atomic nucleus actually has more energy, potential energy, than the electrons closer. And basically Bohr found this out. And the third rule of Bohr is that when electrons move from orbital to another, so if they move from orbital to another, they emit or absorb energy. So if an electron that is here would move into a closer layer, due to the fact that it is being reduced of energy, it produces energy. But if an electron here would be moving out, due to the fact that it's gaining energy, or the energy of this electron is increasing, it absorbs energy. Alright, so this is basically what the Bohr model or planetary model represents. Now, although we do use this Bohr model quite often in chemistry, it was actually proven incorrect by this mathematician called Heinsberg. And Heisenberg basically introduced the uncertainty principle, and you know how Bohr basically said that electrons exist in these certain areas called orbitals. And Heisenberg basically proved mathematically that it was impossible to know the exact position or where electrons were. And this introduced a new concept called orbitals. And the orbital model of an atom is the most accurate representation of an atom we currently have up to today. And basically what orbitals are is, due to the fact that we can't know for sure where these electrons are, Heisenberg basically said that there can be this area. So if this is the atomic nucleus, there can be these areas that we can guess that electrons would probably be in this area. So we call these areas orbitals. And as I said before, orbitals are where scientists think or guess electrons would be, most probably or most commonly. And there will be another video on orbitals, because that is just another very deep rabbit hole that is very complicated. And so if you want to know about orbitals, you could watch that. And that is it for the progress of how atom, or the autonomy of the atom, progressed through the years. And to sum it all up, the first scientist that introduced the idea of atoms was, as we see here, Dalton. Now, Dalton first introduced the idea of atoms, and he proposed 4 theories, in which 2 were correct. And his model of the atom was just basically this bland ball that he thought was filled of something. Now, after Dalton, as we can see, the next scientist is Thompson. And Thompson stated that there were actually electrons within these atoms. So he believed that electrons were kind of like in random formations, kind of like embedded into an atom. And we often call this the electron pudding model, because it kind of, Thompson believed that electrons were kind of stuck to the atom in such a way. Now the next person to progress the study of atoms was Rutherford with his gold foil experiment. Rutherford. And with this gold foil experiment, he discovered the existence of nucleuses. And so the model of an atom progressed even more, and he believed that there were these nucleus and electrons were kind of like surrounding it. Very similar to Thomson's. Now, from then, it becomes more accurate when the scientists named Bohr introduces the idea of orbits, or electron shells. So there would be the atomic nucleus here, and electrons would exist on these shells, these outer shells. But then even Bohr was proven wrong by Heinsberg's uncertainty principle, and with math he proved that we cannot determine, or it is impossible to determine, the exact location of electrons, and so orbitals were introduced, and there would be another episode concerning orbitals. And so this is kind of the summary view of how the atom progressed throughout the years. And that is it for the history of how the atom progressed.